And now in this lecture we'll find out the area of trapezoid ABCD. In the drawing we have a circle that is inscribed by trapezoid ABCD. In addition, you know that side AB of trapezoid ABCD equals to x, side DC equals to x over 7. This is angle DAB, that is a right angle, and this is angle ABC, that is also a right angle. Again, our mission is to find out the area of this trapezoid ABCD. So, first of all, what is a trapezoid? Trapezoid is a quadrilateral with one pair of parallel sides. Again, trapezoid is a quadrilateral with one pair of parallel sides. So in the drawing we have trapezoid ABCD. Trapezoid ABCD is a quadrilateral with one pair of parallel sides. This is to say side DC is parallel to side AB, and for that reason this quadrilateral is a trapezoid. And what is the area of trapezoid ABCD? The area of trapezoid ABCD, first of all, the two parallel sides, that is to say side DC that is parallel to side AB, those two sides are defined as the bases of the trapezoid. So DC is one base and AB is the other base. So the area of this trapezoid ABCD equals to the sum of its bases. That is to say it is DC plus AB. But according to our definition, DC is A and AB is B, and therefore DC plus AB equals to A plus B times the height, that is H, over 2. Again, the area of this trapezoid ABCD equals to the sum of its bases, that is A plus B, times the height, that is H, over 2. The height H must create 90 degrees with the two bases. Here, this angle equals to 90 degrees, and this angle also equals to 90 degrees in its size. Again, the area of this trapezoid ABCD equals to the sum of its bases, that is A plus B, times the height, that is H, over 2. Repeat again that the height H must create 90 degrees with the two bases. Okay? So, first of all, we will define the points of tendencies, the points of tendency of this trapezoid ABCD with this circle with letters. That is to say, we define the point of tendency of tangent AB, of side AB with this circle, this point, as E. Likewise, we define the point of tendency of tangent AD or side AD with this circle, this point as F. Likewise, we define the point of tendency of tangent BC or side BC of the trapezoid with this circle, this point as G. And finally, we define the point of tendency of tangent DC or side DC with this circle, this point as H. So here we can implement rule 2. I'll repeat quickly on rule 2. According to rule 2, the lengths of two tangents from a common external point to a circle are equal. So in the drawing we have a circle, and this is the common external point, point P. From this common external point, point P, we have two tangents to this circle. We have tangent PA, tangent PB. And according to rule 2, they are equal to each other. That is to say, PA equals to PB. So whenever you draw from a common external point two tangents to a circle, then the lengths of two tangents must be equal to each other. In this case, PA equals to PB. So we can actually implement rule 2 in our drawing. Why? Because in our drawing, we have this is the common external point, point A. From this common external point, point A, we have two tangents to this circle. We have tangent AF and tangent AE. and according to rule 2 they are equal to each other. That is to say AF equals to AE. So if we define the length of this tangent AE as y, then the length of tangent AF must be also equal to y according to rule 2 because they are equal to each other. That is to say AE equals to AF. Likewise, if we focus on this common external point B, from this common external point B, we have two tangents to this circle. We have tangent BE and tangent BG. And according to rule 2, they are equal to each other. That is to say, BE equals to BG. So if we define the length of tangent BE as Z, then the length of tangent BG must be also equal to Z, because they are equal to each other according to rule 2. Likewise, if we focus on this common external point C, from this common external point C, we have two tangents to this circle. We have tangent CG and tangent CH. And according to rule 2, they are equal to each other. That is to say, CG equals to CH. So if we define the length of this tangent CG as M, then the length of this tangent CH must be also equal to M, because they are equal to each other. And finally, if we focus on this common external point D, from this common external point D, we have two tangents to this circle. We have tangent DH and tangent DF. And according to rule 2, they are equal to each other. That is to say, DH equals to DF. So if we define the length of this tangent DH as T, then the length of this tangent DF must be also equal to T, because they are equal to each other. Okay, so in the next step we will add side AB to the opposite side, side DC. Again, we will add side AB to the opposite side, side DC in this trapezoid AB CD. So what is the value of AB plus DC? AB plus DC. AB, from now it is very easy to see that AB in total equals to y plus z. Again, AB equals to y plus z plus DC. From the door it is very easy to see that DC in total equals to T plus M. Again, DC equals to T plus M. In conclusion, actually found out that AB plus DC equals to y plus z plus T plus M. Likewise, we will add side AD to the opposite side, side BC. So it is AD plus BC. AD plus BC. So, what is the length of side AD? Side AD equals to y plus t. Side AD equals to y plus t plus BC. BC equals to z plus m. So in total we found out that AD plus BC equals to y plus t plus z plus m. So here we can change the orders of the letters here because of the fact that we have the algebraic identity that a plus b equals to b plus a. Therefore, instead of y plus t plus z plus m, we can write here y plus z plus t plus m. We only change the orders of the letters, we didn't change anything else, only the order of the letters here. So actually found out that AD plus BC equals to y plus z plus t plus m, and AB plus DC also equals to y plus z plus t plus m. And therefore, because of the fact that those two expressions they are both equal to this expression, it means that those two expressions must be equal to each other. That is to say, AB plus DC must be equal to AD plus BC. Okay. So here we have AB. AB is x according to what is given us the question, so we substitute AB by x plus DC. DC is 7 over x according to what is given us the question, so we substitute DC by 7 over x. So in this side of the question 1 we have x plus 7 over x, and it is equal to AD. Here we define side AD of this trapezoid ABCD as A. Side AD equals to A according to our definition. Likewise, we define side BC of this trapezoid ABCD as B. BC equals to B according to our definition. And therefore, AD equals to A plus BC equals to B. So in total, actually found out that according to equation 1, x plus 7 over x equals to A plus B. Again, x plus 7 over x equals to A plus B according to equation 1. In the next step, we do a construction. That is to say, from point B, we will do perpendicular on DC. Again, from point B, we will do perpendicular on DC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B and DC as point S. Okay, by doing this construction, we actually created a quadrilateral ABSC. This is quadrilateral ABSC. Inside this quadrilateral ABSC, we have 1, 2, 3 right angles. Again, inside quadrilateral ABSC, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle. In total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, the fourth missing angle, this fourth missing angle, must be equal to 90 degrees in its size. So inside quadrilateral ABSC, we have 4 right angles. And we know that any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to this quadrilateral ABSD as a rectangle. So I write it down. This quadrilateral ABSD is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABSD, side AB must be equal to the opposite side DS. Again, in rectangle ABSD, side AB must be equal to the opposite side DS. But AB is x, according to what is given as the equation, therefore DS must be also equal to x. Likewise, according to the same rule, in the same rectangle ABSD, side AD must be equal to the opposite side BS. But AD is A according to our definition. Therefore, BS must be also equal to A. By doing this construction, we created here the right triangle, triangle BSC. This is the right green triangle, triangle BSC. So in the right green triangle, triangle BSC, you just write down found out that side BS equals to A. The hypotenuse BC equals to B. So what is the length of this side SC from the drawing? It is very easy to see that SC in total equals to DC minus DS. Again, SC equals to DC minus DS. So I write it down. SC in total equals to DC minus DS. So SC equals to DC, that is actually 7 over X, minus DS, that is X. So in total, we actually found out that SC equals to 7 over X minus X. So this is side SC, that is equals to 7 over X minus X. So in the next step, I'll copy this right triangle BSC in a new page, and we will implement the Pythagoras theorem on this right triangle BSC. Here by PT is the abbreviation for Pythagoras theorem. So we just find out that side SC equals to 7 over X minus X. Side BS of the right triangle BSC equals to A. And finally, the hypotenuse BC equals to B, according to our definition. So actually, this is the right triangle BSC that I copied from the original drawing. Here by PT is the equation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in this right triangle BSC, the hypotenuse is BC, and therefore the square of the hypotenuse is BC squared, and it must be equal to BS squared plus SC squared. This is equation 2, according to Pythagoras theorem. BC squared equals to BS squared plus SC squared. So BC, the hypotenuse BC is B, therefore BC squared is B squared, and it is equals to BS squared. BS is A, therefore BS squared is A squared plus SC squared. SC is 7 over X minus X, therefore SC squared is 7 over X minus X squared. So we have here this expression 7 over X minus X squared. So we use the following algebraic identity that states that A minus B squared is equal to A plus B squared minus 4 times AB. So we use this algebraic identity for this expression 7 over X minus X squared. And we get that according to this equation 2, B squared equals to A squared plus 7 over X minus X squared. According to this algebraic identity, 7 over X minus X squared, if we just substitute A by 7 over X and B by X, we get that 7 over X minus X squared according to this algebraic identity will be equal to 7 over X plus X squared minus 4 times 7 over X times X. Okay? So actually found out that b squared equals to a squared, and here we have plus 7 over x plus x squared. Here we have x over x is 1, so x will get cancelled, and we're left only with minus 4 times 7, that is minus 28. So in this equation 2 we have this expression 7 over x plus x. But according to equation 1, we have already found out that 7 over x plus x is equals to a plus b. Therefore, we can substitute 7 over x plus x in this equation 2, by a plus b from this equation 1. We'll do it now, and we get that according to this equation 2, we have here b squared, that is equal to a squared, plus 7 over x plus x is a plus b, and therefore 7 over x plus x squared will be equal to a plus b squared minus 28. So actually found out that according to equation 2, b squared equals to a squared plus a plus b squared minus 28. Here we'll open the brackets of this expression, and we get that according to this equation 2, b squared equals to a squared plus a plus b squared equals to a squared plus b squared plus 2 times a times b minus 28. So here we have b squared on both sides of the equation, so b squared will get cancelled. After we cancel b squared, in this side of the equation we left with nothing, that is to say 0, that is equals to a squared plus a squared is 2a squared, and we have here plus 2ab minus 28. So here we add 28 to this equation 2, and we get that according to this equation 2, 28 equals to 2a squared plus 2ab. Here we divide this equation 2 by 2, and finally we get that according to this equation 2, 28 over 2 is 14, and it is equals to 2a squared over 2 is a squared, plus 2ab over 2 is ab. So in conclusion, we actually found out that according to this equation 2, 14 equals to a squared plus ab. This is according to equation 2, while according to equation 1, we have already found out that x plus 7 over x equals to a plus b. So in the next step, we'll find out the area of trapezoid ABCD according to the equation that I presented to you in the beginning of the lecture. So the area of this trapezoid ABCD is equal to the sum of its two bases. The two bases must be parallel to each other. Here we have square rectangle ABSD. In this rectangle ABSD, side AB is parallel to the opposite side DS. Again, AB is parallel to the opposite side DS in rectangle ABSD. But DS is part of the straight line DC. Again, DS is part of the straight line DC, and DS is parallel to AB, and therefore the straight line DC itself must be also parallel to AB. In conclusion, we found out that the DC is parallel to AB, and therefore The two parallel sides are AB and DC, and they are defined as the bases of this trapezoid ABCD. So the sum of the two bases are AB plus DC times the height. The height must create 90 degrees with the base. And again, indeed, side AD indeed creates 90 degrees with the base AB, and it creates 90 degrees with the base DC. And therefore, AD is the height of the base. So it is the sum of the two bases, that is BC plus DC, times the height of the base, that is AD, over 2. Okay, so AB equals to x, the base AB equals to x according to what is given as the equation, plus DC. DC equals to 7 over x according to what is given as the question. So actually, AB is x, DC is 7 over x, times AD, times the height AD. AD is A according to our definition, divided by 2. So here we have x plus 7 over x. But we have already found out that according to this equation, equation 1, x plus 7 over x equals to a plus b. So we can substitute x plus 7 over x in this expression by a plus b. We'll do it now. So x plus 7 over x is a plus b times a over 2. So here we'll open the brackets of this expression, and we get that the area of trapezoid ABC equals to a times a is a squared plus AB over 2. But we have already found out that a squared plus AB according to this equation, equation 2, equals to 14. Therefore we can substitute a squared plus AB by 14 according to equation 2. We'll do it now, and we get that a squared plus AB is 14 over 2, and 14 over 2 is 7. So we actually found out that the area of trapezoid ABCD is equal to 7 square units. And that is the answer to the question. I repeat again, the area of this trapezoid ABCD equals to 7 square units. So in the next step, I will summarize the lecture. In this lecture, we found out the area of this trapezoid ABCD. So, in the drawing, we have this circle that is inscribed by this trapezoid ABCD. In addition, we know that side AB of trapezoid ABCD equals to x, side DC equals to 7 over x. This is angle BAD, that is a right angle. This is angle CDA, that is also a right angle. Again, our mission is to find out the area of this trapezoid ABCD. Okay, so I repeat again. We actually found out what is the definition of a trapezoid. Trapezoid is a quadrilateral with one pair of parallel sides. I repeat again. Trapezoid is a quadrilateral with one pair of parallel sides. So in the drawing we have, this is quadrilateral ABCD, and in this quadrilateral ABCD, side DC is parallel to side AB, and therefore this quadrilateral is defined as a trapezoid. So ABCD is a trapezoid. And we know, because of the fact that side DC is parallel to the opposite side AB, those two parallel sides are defined as the bases of this trapezoid. So DC is the base and AB is the other base. But DC is A according to our definition, AB is B according to our definition, and therefore the area of this trapezoid ABCD equals to the sum of its bases. That is actually DC plus AB, but DC is A and AB is B, and therefore DC plus AB is A plus B, times the I to the base. The I to the base must create 90 degrees with the base, so here H creates 90 degrees with the two bases, over 2. Again, the area of this trapezoid ABCD equals to the sum of its bases, that is A plus B, times the ith edge over 2. Okay? So, first of all, we actually define the points of tendency of this trapezoid ABCD with this circle with letters. We define the point of tendency of tangent AB of side AB with this circle as E, this point. We define the point of tendency of tangent BC of side BC with this circle, this point as G. We define the point of tendency of side AD of tangent AD with this circle as F. And finally, we define the point of tendency of tangent DC or side DC with this circle, this point as H. So here we can implement rule 2. Repeat quickly on rule 2. According to rule 2, the lengths of two tangents from a common external point to a circle are equal. So we have here this circle, and we have this is common external point, point P. From this common external point, point P, we have two tangents to this circle. We have tangent PA and tangent PB. And according to rule 2, they are equal to each other. That is to say, PA equals to PB. So whenever you draw two tangents to a circle from a common external point to the circle, then the lengths of two tangents must be equal to each other. In this case, PA equals to PB. You can actually implement rule 2 in our drawing. In our drawing, if you focus on this common external point, point A is an external point in relation to this circle because it is not located inside this circle nor on the circle. It is located outside this circle, and therefore, in relation to this circle, it is defined as a common external point. So from this common external point, point A, we have two tangents to this circle. We have tangent AF and tangent AE, and according to rule 2, they are equal to each other. That is to say, AF equals to AE. Okay? So if we define the length of this tangent AF as y, then the length of AE must be also equal to y because they are equal to each other, according to rule 2. Likewise, if you focus on this common external point, point B, from this common external point, point B, we have two tangents to this circle. We have tangent BE and tangent BG. And according to rule 2, they are equal to each other. That is to say, BE equals to BG. So if we define the length of tangent BE as Z, then the length of tangent BG must be also equal to Z because of the fact that BE equals to BG. Likewise, if you focus on this common external point, point C, from this common external point, point C, we have two tangents to this circle. We have tangent CG and we have tangent CH. And according to rule 2, they are equal to each other. That is to say, CG equals to CH. So if we define the length of CG as M, then the length of CH must be also equal to M because they are equal to each other. And finally, if we focus on this common external point, point D, from this common external point, point D, we have two tangents to this circle. We have tangent DH and tangent DF. And according to rule 2, they are equal to each other. That is to say, DH equals to DF. So if we define the length of tangent DF as T, then the length of tangent DF must be also equal to T because they are equal to each other according to rule 2. So in the next step, we added side AB to the opposite side DC. Again, AB plus DC. So AB equals to Y plus Z. DC equals to T plus M. So in total, AB plus DC equals to Y plus Z plus T plus M. Again, AB plus DC in total equals to Y plus Z plus T plus M. Likewise, we added side AD to the opposite side, side BC. Side AD equals to Y plus T. Side BC equals to Z plus M. So in total, AD plus BC equals to Y plus T plus Z plus M. Repeat again. AD plus BC in total equals to Y plus T plus Z plus M. Okay. Here we can change the order of the letters here according to the algebraic identity that A plus B equals to B plus A. So we can change the order here. Instead of Y plus T plus Z plus M, we can write down Y plus Z plus T plus M. We change only the order, so it is allowable. So this expression AD plus BC equals to Y plus Z plus T plus M, and B plus DC also equals to Y plus Z plus T plus M. So those two expressions are equal to the same further expression, and therefore they must be equal to each other. That is to say, AB plus DC must be equal to AD plus BC. Okay, AB equals to X according to what is given in the equation. DC equals to 7 over X according to what is given us in the question. So AB is X, DC is 7 over X, AD is A according to our definition, and BC is B according to our definition. Again, AD is A and BC is B. So actually, according to equation 1, we actually found out that X plus 7 over X equals to A plus B. Okay? In the next step, we did a construction. That is to say, from point B, we do perpendicular on DC. Again, from point B, we do perpendicular on DC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B and DC as point S. By doing this construction, we created a quadrilateral ABSD. Inside this quadrilateral ABSD, we have 1, 2 free right angles. The sum of free right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle. In total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside this quadrilateral ABSD, we have 4 right angles, and you know that any quadrilateral that has 4 right angles must be a rectangle, if not a square. So we relate to this quadrilateral ABSD with 4 right angles as a rectangle. And you also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABSD, side AB equals to the opposite side DS. But AB is X, according to what is given in the equation, therefore this DS must be also equal to X. Likewise, according to the same rule, in the same rectangle ABDS, side AD must be equal to the opposite side BS. But AD is A, according to our definition, therefore BS must be also equal to A because they are equal to each other. Okay, so by doing this construction, we actually created here the right green triangle, triangle BSC. We have already found out that side BS of the green triangle equals to A, the hypotenuse BC equals to M. So what is the length of this side SC? From the drawing, it is very easy to see that SC equals to DC minus DS. Again, SC equals to DC minus DS. SC equals to DC minus DS. DC is 7 over X according to what is given as the equation. DS is X. So in total, DC minus DS is 7 over X minus X. Therefore, SC equals to 7 over X minus X. In the next step, I copy this right green triangle, triangle BSC in a new page, and we implemented the Pythagoras theorem on this right green triangle, triangle BSC. So really, this is the right green triangle, triangle BSC that I copied from the original drawing. Here by PT is the version for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse on this right triangle BSC is BC, and therefore the square of the hypotenuse is BC square, and it must be equal to BS square plus SC square. Again, BC square equals to BS square plus SC square according to the Pythagoras theorem. BC is B, therefore BC square is B square. BS is A, therefore BS square is A square plus SC square. SC is 7 over X minus X, therefore AC square is 7 over X minus X square. Here we use the algebraic identity that A minus B square equals to A square plus B square minus 4 times AB. If you just open the brackets on both sides, you will definitely see that those two sides of the equation are equal to each other. So we use this algebraic identity for this expression 7 over x minus x squared. So according to equation 2, I should find out that b squared equals to a squared, and here we have 7 over x minus x squared. And according to this algebraic identity, 7 over x minus x squared, if you just substitute a by 7 over x and b by x, you will get that 7 over x minus x squared will be equal to 7 over x plus x squared minus 4 times 7 over x times x. Again, if you just substitute a by 7 over x and b by x, you get that 7 over x squared, according to this algebraic identity, will be equal to 7 over x plus x squared minus 4 times 7 over x times x. So here we have x in the numerator and x in the denominator, so x will get cancelled. So according to equation 2, we should find out that b squared equals to a squared plus 7 over x plus x squared. Here x will get cancelled, and we left only with minus 4 times 7, that is minus 28. So according to equation 2, we should find out that b squared equals to a squared plus 7 over x plus x squared minus 28. But this is according to equation 2, but according to equation 1, we have already found out that 7 over x plus x equals to a plus b. Therefore, we can substitute 7 over x plus x in this equation 2 by a plus b from equation 1. We did it, and we actually found out that according to this equation 2, b squared equals to a squared plus a plus b squared minus 28. We just substitute 7 over x minus x squared by a plus b squared. Okay. Here we open the brackets on this side of the equation and found out actually that b squared equals to a squared and a plus b squared equals to a squared plus b squared plus 2 times ab minus 28. Here we have b squared on both sides of the equation 2. Therefore b squared will get cancelled. As we cancel b squared, in this side of the equation we left with nothing, that is to say 0. And it is equals to a squared plus a squared is 2a squared plus 2ab minus 28. Here we added 28 to this equation 2, and found out that according to equation 2, here we have 0 plus 28 is 28. This equals to 2a squared plus 2ab. Here we divided this equation 2 by 2, and finally found out that 28 over 2 is 14. 2a squared over 2 is a squared, and 2ab over 2 is ab. So in conclusion, according to equation 2, we actually found out that 14 equals to a squared plus b squared. This is according to equation 2, while according to equation 1, we have already found out that x plus 7 over x equals to a plus b. So we have here two equations. And what is the area of trapezoid ABCD? The area of this trapezoid ABCD, according to the equation that I presented to you, the formula that I presented to you in the beginning of the lecture, the area of this trapezoid ABCD equals to the sum of its two bases, and the two bases are parallel to each other. Here we know that in the rectangle ABCD, side AB is parallel to the opposite side DS. It is true in any rectangle, and especially it is true in rectangle ABDS. The opposite sides are parallel to each other. AB is parallel to DS, but DS is part of the straight line DC and is parallel to AB. Therefore, the straight line DC itself must be also parallel to AB. So we know that in trapezoid ABCD, side AB is parallel to side DC. Therefore, the two bases are AB and DC because they are parallel to each other. So the sum of the two bases are AB plus DC. Again, the sum of the two bases that are AB plus DC times the height to the base. The height to the base must create 90 degrees with the two bases. If DA equals to 90 degrees with the base AB, and here this DA also creates 90 degrees with the other base DC. Therefore AD is the base, is the height. is AD is the height to the base because it creates 90 degrees with the two bases. So the height is AD. Again, the area of trapezoid ABCD equals to the sum of the two bases, that is AB plus DC, times the height, that is AD, over 2. AB is X and DC is 7 over X, according to what is given as the question. AD is A according to our definition. AD is A divided by 2. So in total, we found out that X plus 7 over X times A over 2 is the area of this trapezoid ABCD. But according to equation 1, we have already found out that X plus 7 over X is A plus B. So we can substitute X plus 7 over X by A plus B. We did it and found out that X plus 7 over X is A plus B times A over 2. Here we open the brackets of this expression and found out actually that A times A is A squared plus AB over 2. But according to equation 2, A squared plus AB is 14. Here, according to equation 2, A squared plus AB is 14. Therefore, we substitute A squared plus AB here by 14. And finally found out actually that the area of trapezoid ABCD equals to 14 over 2, that is 7. Repeat again, we found out actually that the area of this trapezoid ABCD is equals to 7 square units. Okay, thank you very much.